We're ready for the last section out of chapter 3. In this section, we talk about motion in space. Now, we've already described how to find arc length and curvature. We've been looking at calculus with vector valued functions. And all of this leads to the primary goal of this particular chapter, which is the description of motion along either a plane curve in a two-dimensional space or along a space curve in three-dimensional space. We have all the tools we need. We're just going to need to put them all together. Now, so far, what we want to do is we want to take a vector valued function and let the vector valued function represent our position of a particle moving in either three-dimensional space or two-dimensional space. All of the material that we're going to learn in this section can be applied to either 2 dimensions or 3 dimensions, plane curves or space curves. For example, let's think about the orbit of the planets, all right, around the sun. In fact, although they exist in 3-dimensional space, their motion around the sun is actually occurring in a plane because their orbits are all elliptical. They're occurring in a 2-dimensional space, even though the object itself is in 3 dimensions. On the other hand, have you ever been in a parking garage where you have to travel around and around and around in a curving pattern to go from one floor to the next? That shape is a helix pattern. And that helix pattern, of course, not only exists in 3-dimensional space, but the motion of your car as you drive up that ramp is also in 3-dimensional space. And we want to be able to describe the motion, the velocity and acceleration in those particular spaces. We only have a couple of learning objectives here, which is to describe the velocity and acceleration vectors of a particle moving in space. And again, we have motion, so we have both magnitude and direction. So we will be using vector valued functions. The second thing we're going to do is we're going to take the acceleration vector, which is going to be somewhat different than in the previous section, and we're going to split it into 2 components. Now, in the previous section, we talked about the unit tangent vector, the unit binormal vector, and the unit normal vector. Because we were dealing only with circles, the acceleration vector always pointed along the radius of the osculating circle along the normal vector. If it's not moving in a circular pattern, then the acceleration vector will not lie wholly on top of the normal vector. In other words, you'll be able to split it into 2 components, one along the unit tangent vector and one along the unit normal vector. The acceleration vector does still lie within the osculating plane, where that circle is that determines the curvature at a particular point. I'm going to go ahead and share my screen with you, and we'll get started with motion in space. Okay, from Calculus 1, we know that the position of a particle can be described with a function. And if we want to find the velocity function, we take the derivative of the position function. And if we want to find the acceleration, we take the derivative of velocity or the second derivative of position. In this particular case, we're now moving into 2 and 3 dimensions. So if we use a vector valued function, r of t, to represent our position, then we can find the velocity function, v of t, as r prime of t. And the acceleration function, which is the derivative of velocity, v prime of t, becomes r double prime of t. Note that r of t can be in either 2 dimensions or 3 dimensions. Now, speed is still a scalar. Remember that a vector has position, direction, and it also has magnitude. When we say speed, like the speedometer in your car, you're not talking about velocity. You're talking only about the magnitude of the velocity. 60 miles per hour is 60 miles per hour in any direction. That's magnitude. 60 miles per hour north, that's velocity. So since speed is a scalar, we'll use the letter V to represent it, but it won't be bolded. Now, when you're typing, it can be a little confusing because you got to be sure that you can tell what is bolded and what is not. I actually find it easier when we handwrite because speed will not have the vector notation above it, or the harpoon. So if we want to think about speed, which is this v of t, which is not bolded, so let me go ahead and write this down so that we are clear on what this is. This is speed, which is v of t without the bolding. It is the magnitude of the vector representing velocity, which is the magnitude of the derivative of the position vector. If we want to do it in terms of arc length, as we discussed in a previous section, we can write it as ds dt, where s is still the arc length parameterization. And again, remember that the arc length parameterization is the integral using the fundamental theorem of calculus from some finite value a to some unknown variable t, the integral of the magnitude of r prime of t, or r prime of u du, where u is a dummy variable. Since we have these relationships, we can go ahead and note down what the formulas would be in both 2 dimensions and 3 dimensions. So in this table right here, I've given you the position, velocity, speed, and acceleration formulas in both 2 dimensions in column 2 and 3 dimensions in column 3. I did them in both unit vector notation with I hat and j hat, and I did them in the angle bracket notation. I'll go ahead and take a look at the 3-dimensional case, since the 2-dimensional case is just a simpler one. We let r of t represent the position of the particle moving in 3-dimensional space, where each component of the unit vectors is a real valued function of t. You put in a real number for t, it spits out a real number, and that real number becomes the component of that unit vector, representing the vector valued function r of t. In order to find the velocity of it, you take the derivative of r of t, which we can notate with a bolded letter v, as in Victor. Then what we do is we take the derivative of each of the real valued function components of the unit vectors. In order to find the speed, which is v of t, but without the bolding, the magnitude of v of t, which of course, and I can go ahead and write this here, is the magnitude of r prime of t, becomes the square of each of the derivatives added together, and then take the square root of the whole thing. This will give us the speed at which the particle is traveling at a particular moment in time, where we choose the moment in time with the value of the parameter t. A of t is also a vector, so the letter A is in bold. And this becomes the second derivative of the position vector. So it becomes x double prime of t, y double prime of t, and z double prime of t. Note that in here, instead of using f of t, g of t, and h of t, we are using x as a function of t, y as a function of t, and z as a function of t. This is relatively common when you're in 3-dimensional space and you're describing motion in that space. We measure space in terms of relationship to the x-axis, the y-axis, and the z-axis. So giving those positions, representing them with the coordinate axes variables, in a sense, makes it more possible to understand where the particle is at a moment in time. Let's take a look now at example 1. In example 1, we have a particle moving in a path defined by a vector valued function r of t. R consists of t squared minus 3t in the first component, I hat, 2t minus 4 in the second component, j hat, and 2 plus t in the third component, k hat. T again measures time, this time in seconds, and our distance is going to be measured in feet. We want to find the velocity, the acceleration, and the speed as functions of time. Now, velocity and acceleration will be vectors, but speed will not. It will be a real valued function of t. So go ahead and pause the video, work out the solutions, then turn the video back on and we'll compare our results. So let's see how you did. This is relatively straightforward. What we're doing is simply taking the derivative. So to get the velocity vector, note the harpoon notation over the letter V, is r prime of t, which gives us 2t minus 3 in the first component, the I hat direction, 2 in the second component, j hat direction, and 1 in the third component, k hat direction. The easiest thing is to go ahead and compute the acceleration vector, because the acceleration vector, again, using the harpoon notation over the A, is the first derivative of velocity and the second derivative of the position vector. In that case, the derivative with respect to the parameter t gives me 2, 0, 0. In other words, 2I hat becomes the acceleration vector. Now, speed is given by the magnitude of the velocity vector, which was our first row. So we take each component, square it, add them together, and take the square root. Note that when you multiply out 2t minus 3, you always end up with 3 terms. Don't square each one individually and think you're done. The outside and inside products do not cancel, they double. So you get 4t squared minus 12t plus 9. And then when you square the second two components, you end up with plus 4 plus 1 or plus 5, so that your final speed is given by the square root of 4t squared minus 12t plus 14. Notice that this letter V does not have the harpoon over the top. It is not a vector. It is a real valued function of t. Let's go ahead and take a look at the picture of this. You can see right here what it looks like in this picture, and I'll show it to you in CalcPlot 3D. There is a link right here, and this is calculated when t is equal to 2. The green arrow represents the acceleration, and the black arrow is the velocity. The velocity, again, is the tangent vector. Not necessarily the unit tangent vector, but the tangent vector. Let's take a look at what it looks like over here. So we can see it from different angles. And if we wanted to, we could go ahead and move the slider bar in the trace box, and we could see how it changes. Now, if you want to see where the normal vector is pointing, click on the gear symbol and come over and tell it to plot the unit normal, and maybe you want to see the unit tangent as well. Note here that the unit tangent does lie along the tangent vector. The unit tangent vector is represented in a violet purple color, whereas the unit normal is blue. Because our curve is not circular as it was in the previous ones, the acceleration vector in green does not lie completely on top of the normal vector. It can be split into two components, one along the unit tangent vector and one along the unit normal. And I'm trying to get it to a spot where you can see that they're not the same. You can tell these are different. Of course, you kind of lose the color when you turn it that way. Green maybe is not the best color for the acceleration vector. All right, remember that velocity and acceleration are vectors. We studied this extensively in Calculus 1, and I hope that you will remember that velocity can change even when the speed is constant. Let me say that again. Velocity can change even when the speed stays constant. If you're driving around a curve, but you maintain the same speed around the curve, say 60 miles per hour, you're still changing velocity because you're changing direction, right? So again, your speed is a constant 60 miles per hour, but your velocity as it changes direction changes. Let's take a look at this picture right here, which gives some indications of which directions the velocity vectors are pointing in as the car moves along this winding curvy road. When the car is at the initial point of the velocity vectors, then they have drawn the line here. So this first red arrow to the left actually has the car positioned at the initial point of the vector. And when the car is at that point, the velocity vector is pointing in that direction. Where the car is currently shown is at the initial point of the second red vector. And at this point in the curve, the velocity vector is pointing in this direction. However, as the car progresses around the curve so that the car is at the initial point of the third vector, the velocity vector points in a different direction. All three of the red arrows are the same length, so the speed is the same, but the velocity is different in each location because the direction is different. What we want to do now is we want to think about that acceleration vector. We saw that when the path was circular, and we looked at several circular shapes in the previous section, that the acceleration vector lay directly on top of the unit normal vector. However, we're now allowing for motion in space not along a circular section, in which case, if it's not along a circular section, the acceleration will not point directly along the unit normal. It will still lie within the osculating plane. Let's take a look over here at our picture again. Let's click on the gear symbol and let's add this osculating plane. Now, if I come over here, if you use your scroll bar, you can make the picture larger without zooming in or out. When you look at it like this, do you see that that yellow plane contains both the unit normal and the unit tangent? And our acceleration vector lies along that plane. Let's move it to a different point so it's a little more obvious it's in the plane. There we go, right there, right? Now, no matter how I turn it, and if I turn it like this, so it's almost sideways, you can see that the green arrow is inside that yellow plane. That's called the osculating circle right there, because again, if you want to click on the gear symbol and you want to show the osculating circle up at the top, you'll see where it is right there. So there's your osculating circle. It's quite large at this point. The curvature is not very great. What we want to do then is we want to split the acceleration vector into two components. Remember that the TNB framework, the Frenet frame, provides a sort of three-dimensional coordinate system at the point in space where the object is. So we want to take the acceleration vector, which is lying in the plane spanned by the unit tangent and the unit normal vector, and we want to split it into components that lie parallel to one of those two vectors. So we want to split it into two components, a sub t, one tangent to the curve, and a sub n, one along the normal, so orthogonal to the curve at that point. Now remember that the t and the n form that osculating plane with the osculating circle at a particular point on the position vector. The binormal is orthogonal to both, which gives us our third dimension, right? If the curve is circular, as in the previous section, the acceleration vector lies on top of the normal vector, and there will be no component along the tangent vector. If the curve is completely linear at a particular point, then the acceleration vector lies completely on top of the unit tangent vector, and there's no component of it in the unit normal direction. Let's go ahead and use these two components of acceleration to represent our acceleration as a linear combination of the unit tangent and the unit normal vectors. So we can write A as a vector of t becomes v prime of t times the unit tangent vector plus v of t quantity squared times the curvature kappa times the unit normal vector, right? Now, this is the formula that gives us the acceleration written in terms of the two vectors, the unit tangent vector, the unit normal. So the one along the unit tangent, this is our a sub t, the portion of the acceleration along the tangent vector. And the second term is our a sub n, the portion of acceleration that lies along the normal vector. Recall that v of t without the bolding or the harpoon represents speed of the object. So the coefficients here of the unit vectors are all scalar valued functions, real valued functions of t. This is the derivative of speed, v prime of t, and this is the speed squared, v of t squared. All right, so let's go ahead and notate that here. Derivative of speed, that's here, and this is speed squared. Now let's go ahead and prove this particular relationship. All right, so we're going to start with what we know, which is that the velocity vector, this is bolded, the velocity vector is equal to the derivative of the position function, r prime of t. We also know that the unit tangent vector points in the direction of the tangent vector, but is 1 unit long. R prime of t is the tangent vector. So this right here is the tangent vector. It's just not necessarily 1 unit long. To force it to be 1 unit long, we divide it by its magnitude. So the unit tangent vector is r prime of t divided by the magnitude of r prime of t. This tells us that we can rearrange things a little bit, and we can write that v of t, which is r prime of t, is the magnitude of r prime of t times the unit tangent vector. Because the unit tangent vector is divided by the magnitude, they would cancel, and we would get back r prime of t. So it's just a manipulation of factors. However, the magnitude of r prime of t, that's speed. So that gives us our v of t times the unit tangent vector. So this gives us speed here and here, right? Now, the next thing we're going to do is we're going to take the derivative of each side. Why? Because we're looking for the acceleration vector. We have an acceleration vector lying in the osculating plane coming off at an angle to both the tangent vector and the unit normal. We want to take that vector and split it into components that point along the tangent vector and along the unit normal, so that when we add them up, it gives us back the acceleration vector. So we take the derivative of v of t, the velocity. So this is velocity here. And when we take the derivative of velocity with respect to t, we can apply that to our new representation, which is speed times the unit tangent vector. They're both functions of the parameter lowercase t, so we use the product rule. So I get the derivative of speed times the unit tangent vector plus speed times the derivative of the unit tangent vector. And remember, we talked about in a previous video that we don't know how long the derivative of the unit tangent vector is. It's not necessarily still 1. Now we're going to hold off. We're just going to leave this equation here for a moment. I've labeled it 1. And then we're going to define the unit normal vector. The definition of the unit normal vector is the derivative of the unit tangent vector divided by its magnitude. Because we don't know if that unit tangent vector's derivative is 1, then we have to divide by it in order to make it a unit vector. So this is the normal vector, which means that I can rewrite this derivative of the unit tangent vector in terms of the normal vector and the magnitude of the derivative of the unit tangent vector. So it becomes this relationship here in 2. And as you might imagine, we're going to take this relationship that you see here, and we're going to substitute it up in here to replace that part right there. So now we're going to put them together into equation 3. Let me scroll so you can still see everything. So we take equation 2 and substitute it into equation 1. We have the acceleration vector is equal to speed, not bolded, v prime of t times the unit tangent vector, plus speed, not bold, v of t, times the magnitude of t prime of t, the unit tangent vector's derivative, times the normal vector. Now, at this point, we want to go back and pick up one of our formulas for curvature. Remember, curvature is given with the Greek letter kappa, and for a circle, the curvature is the reciprocal of the radius. And the curvature at any point is given by that representation on the osculating circle at that point. So it's the reciprocal of the radius of the osculating circle at that point. And kappa is given by the magnitude of the derivative of the unit tangent vector divided by the magnitude of the tangent vector. So unit tangent vector and tangent vector are related. They lie in the same direction, but they're not the same. So in this case, a unit tangent, not unit tangent's derivative, it doesn't lie in the same direction as that one. Since I have kappa for this part right here, then I can solve for the magnitude of the unit tangent vector's derivative, which gives me kappa times the magnitude of the tangent vector, r prime of t. And the magnitude of r prime of t is just, well, the speed. So this gives me kappa times speed. So I can replace this part up here in equation 3 with kappa times speed. So this part right here, oops, I lost an E, represents speed. And we're going to take this relationship and we're going to substitute it into equation 3 in place of that part right there. And once we replace that, we're given that the acceleration vector is speed, it's derivative, the derivative of speed, unbolded letter v, times the unit tangent vector, plus k times 2 of the speed, which would be speed squared, times the unit normal vector. And this splits it into 2 components. Now, let's go ahead and take a look at a picture in just a moment. So we're splitting it into 2 parts. So when we talk about a sub t and a sub n, what we're talking about is the coefficient of the unit vectors, the unit tangent vector, the unit normal vector. So a sub t does not include the unit tangent vector. It's just the real valued function coefficient, which is the derivative of speed. And a sub n, the normal component of the acceleration vector, is the real valued function kappa for curvature times the speed squared. All right. And these are real valued functions, so they're scalars. So a sub n and a sub t are not vectors. They're multiplied by unit vectors, but they are not themselves vectors. All right. So these are basically the projections of the acceleration vector onto both the unit tangent vector and unit normal vector. Let's see if I have a picture. Here we go. Let's look at the picture first, and then we'll go back up in the notes. The car is here along a curving dotted red trajectory. At this point in time, the velocity vector of the car comes off in this teal color, a bolded letter V. This is the velocity vector. The acceleration, because this curving path is not circular, it does not lie directly on top of the normal vector, which is at a 90-degree angle to the car at that point on the trajectory. So the normal vector is pointing along this blue line out here. The actual acceleration vector is coming off at an angle, and you can see they formed a parallelogram with the acceleration vector, and they've split it into two components. One component is parallel to the velocity vector, which is the tangent vector, which is also in the direction of the unit tangent vector. And then they've split the other component along the normal vector. And if you were to take either a sub n or a sub t and move it to the end of the opposite, you could use the parallelogram method, or you could use the triangle method to prove that a sub t times the unit tangent vector plus a sub n times the unit normal vector equals a, the acceleration vector. So we have a sub t times the unit tangent vector plus a sub n times the unit normal vector gives us the acceleration vector. Now, where are the unit tangent vector and unit normal vector? Well, let me see if I can maybe highlight it a little bit. The unit tangent vector is right there in yellow. And let's do the unit normal vector, same length right here. So they're 1 unit long, and I'm just making up how much 1 unit is, all right, totally at random. But the length of this one and the length of that one are 1, all right? So those become the unit vectors. Let's go ahead now that we've written out this expression for what a of t is, the acceleration vector. Remember that we can replace a sub t with what it's equal to, or a sub t is just derivative of speed. But it turns out that the derivative of speed is actually the acceleration vector dotted with the unit tangent vector. But that means that it's actually the velocity vector times or dotted with the acceleration vector divided by the magnitude of the velocity vector. Because the velocity vector is in the direction of the unit tangent vector, and dividing by its magnitude gives you back the unit tangent vector. So that this part, let me highlight it, this part right here is the definition of the unit tangent vector right there. So it's identical. But we could also write it in terms of the original position vector, that the velocity vector is r prime of t and the acceleration vector is r double prime of t. So we dot those together, and then we divide by the magnitude of r prime of t, which is the magnitude of the velocity vector. So these are really 3 equivalent ways of writing the same thing. All right. Now, when we're looking at it, I will tell you that for most students, the second and the third, or yeah, well, I guess 4th and 5th, which the last 2 are really exactly the same thing. It's just 2 ways of writing it. These tend to be easier to apply than this one. The reason is, in order to dot the acceleration vector with the unit tangent vector, you have to find the unit tangent vector, which means you're going to be working with a vector with probably a very nasty denominator. Whereas over here, you just divide by it at the end and you don't have to work with it along the way. All right. Let's take a look at the normal component of the acceleration vector, which we just proved is the curvature value, kappa, times speed squared, so kv squared. It turns out that this is actually the acceleration vector dotted with the unit normal vector. And if we look at that, there's another way of representing it. Now, these 2 are not identical. They're not actually, I mean, they are identical, they are equivalent, but one doesn't lead directly to the next. What we get is the velocity vector crossed with the acceleration vector, and then we take the magnitude of it and divide by the magnitude of the velocity vector. Now, this fraction and this fraction are identical. Remember that the velocity vector is r prime of t, the acceleration vector is r double prime, and again, this gives us the same relationship. The last expression is different again, but equivalent to the previous 2. It gives us the same thing, or the previous 3. This one can actually be, in some cases, easier to compute if you've already found the tangential component of the acceleration. If you already have a of t, finding the acceleration vector just means taking the derivative twice. and then finding its magnitude and squaring it and subtracting the square of the tangential component of acceleration and then putting the whole thing under a radical is sometimes easier than computing this cross product's magnitude and dividing by the magnitude of the velocity vector. So I recommend for the normal component of acceleration that you use one of the latter two. These tend to be easier to find. A dot, the normal vector, looks like it should be the easiest one, right? It does. It looks like it should be the easiest. It's the easiest formula. But think about what work you have to do to get the unit normal vector. You have to take the derivative of the position vector to get velocity vector. Then you have to divide by its magnitude to get the unit tangent vector. Then you have to take the derivative of the unit tangent vector, and then you have to divide that by the magnitude of the unit tangent vector. Finding the unit normal vector is not a simple case. In most cases, it is simpler to apply one of the latter two. I would apply the last one if I already know the tangential component. Otherwise, I would use one of the two fraction forms, which are identical. All right, let's talk briefly about centripetal or radial component of acceleration. When we talk about this, I don't know if you've ever gone skating, ice skating, or roller skating, and you played the game called Crack the Whip, where you have a line of people skating, holding hands, and the person at the end is getting sort of slung around, right? They feel the acceleration very, very strongly on the end of that whip. The normal component of acceleration has another name, actually two names. It's called the centripetal component of acceleration, or sometimes the radial component of acceleration. Now, why radial? Well, we're talking about the part that lies along the radius of the osculating circle, because the normal vector does lie along the radius of the osculating circle. So it's sometimes called the radial component. Centripetal is a type of force, and it's the force being projected along that vector, right? So it has a different name. So in this picture, we can see that they've labeled it, instead of A sub n, which is what I will typically call it, they've called it A sub r to represent that it's the radial component of the acceleration vector. And what they've done at different points along the car's path is they've shown the acceleration vector as well as its components along the unit normal vector, A sub r, and its component along the tangential vector, or unit tangent vector, A sub t. It also shows the osculating circle at a particular point, and this A sub r lies along the radius of that osculating circle. So it gives you a way of splitting up the acceleration vector into two components that fit within that three-dimensional T and B framework at a particular point. Let's take a look now at example 2. In example 2, we have an object moving in a path defined by a vector-valued function, r of t, where r of t is given by 5t, comma, 1 minus 2t for the j hat component, comma, 4t to the 3/2 power. We want to find the tangential component of acceleration and the normal component of acceleration as functions of t. Remember, these are scalar valued functions. They're real valued functions. They do not include the normal and the tangent vectors. And then we want to find them at a particular point in time. Now, there are, of course, up here, multiple formulas for doing it, but whichever way you want to do it, when you're finding the tangential component, it's they're pretty much all the same, all right? So I've got the solution right there, so you'll be able to know whether or not you got that one right. And after you find the tangential, then I want you to go ahead and find the normal. Now, the normal, you do have different formulas. The two fraction forms are identical, so you could use that. But since you've already got the tangential component, you could also use the last one. So go ahead and pause the video, work out that much of the problem, then turn the video back on so we can compare our results. So let's take a look at this rather long involved problem. We start with our function of position, vector valued function, r of t, 5t, 1 minus 2t, 4t to the 3/2. We want to first find the tangential component of the acceleration, breaking the acceleration into two subcomponents, one along the tangent vector and one along the unit normal vector. When we take the derivative, we get 5 comma negative 2 comma 6 times the square root of t. Taking the derivative again gives us r double prime 0 comma 0 comma 3 divided by the square root of t. To find the magnitude of r prime, I'm applying this last formula here. I square the components of the velocity vector, add them together, and take the square root, which leads to the square root of 36 multiplied by t plus 29. I put this into the formula where I dot the velocity vector with the acceleration vector and divide by the speed, which is the magnitude of the velocity vector. You can see down here at the bottom that I end up with 18 for the dot product of velocity and acceleration, and then I divide by the speed, which is the magnitude of the velocity vector. And this gives me, for the tangential component, the real valued function of t multiplied by the unit tangent vector of 18 divided by the square root of the quantity 36 multiplied by t plus 29. Generally speaking, the tangential component is the easier of the two to find. The normal component is more difficult. Let's take a look at the normal component. There are several formulas that will give you the normal component. You could take and find the curvature and multiply by the square of the speed. You could find the acceleration vector and multiply by the unit normal vector, dot product. Or you can take the velocity vector crossed with the acceleration vector, find the magnitude, and divide by the speed, the magnitude of the derivative of position. Or you could take the square root of the magnitude of the acceleration squared minus the tangential component of acceleration squared. I chose to use the last one first because I already have the tangential component. So I found the tangential component squared, and 18 squared gave me 324 divided by 36 multiplied by t plus 29. Then I needed to find the magnitude of the acceleration vector. The acceleration vector was 0, 0, 3 divided by the square root of t. And when I square each component and add them together, and take the square root of it, then square that, I get 9 divided by t. To find the normal component of acceleration, I use the last formula, and I subtract the square of the tangential component from the square of the magnitude of acceleration. This gives me the difference of two rational functions. So I get a common denominator, and you can see I'm multiplying by a form of 1 in pink so that the denominators match. And then I multiplied it out, and lo and behold, I got a 324t plus 261 minus 324t. So those terms cancel, and I'm left with the square root of 261 over the common denominator, monomial factor t multiplied by binomial factor 36 multiplied by t plus 29. Now, 261 can be reduced because it's 9 times 29, so it becomes 3 square roots of 29, and I've highlighted the solution in yellow. I could also, one of the easier formulas to use is the fractional form. And of course, the two fractional forms are identical. The first two forms generally involve more work and can be a computational nightmare. I highly recommend that you use the last two. So I went ahead and did the second to last formula, which is the magnitude of the cross product of the velocity vector with the acceleration vector divided by the speed, the magnitude of the derivative of position. This gives me a pseudo 3x3 matrix, and I find the determinant. My acceleration vector had two zero components, so it makes sense to expand along row 3 because the first two are just going to zero out. That gives me 3 over the square root of t multiplied by the 2x2 determinant ij 5 negative 2, which gives me negative 2i hat minus 5j hat. And when I multiply it out, I can get the 3 component vector, negative 6 divided by the square root of t, comma, negative 15 divided by the square root of t, comma, 0. To find the magnitude, I square the two non-zero components, add them together, and take the square root, and surprise, surprise, I get a 261 under the radical, which I know reduces to 3 square roots of 29 divided by the square root of t. The normal component using this formula, I then multiply by the reciprocal of the speed, or the magnitude of the tangent vector, the velocity vector, and I end up with exactly the same formula as I did in the first one. Which of these you find easier is somewhat a matter of personal choice, so use the one that makes the most sense to you or that you think will be the most straightforward. We have one last thing to do, which is to find the tangential component and the normal component at a particular point in time. So let's go ahead and rewrite down what the tangential component was, which was 18 over the square root of 36t plus 29. So the tangential component, AT, was 18 divided by the square root of 36t plus 29, right? So if we want to evaluate this, when t is equal to 3, then we would have the following. When the lowercase t is 3, we have 18 over the square root of 36 times 3 plus 29, which when you reduce it gives you 18 divided by the square root of 137, which is about 1.54 feet per second squared in the direction of the unit tangent vector. Then we can apply a similar process and we can substitute into the normal component the value of 3, and this will give us 3 square root of 3 times square root of 29 divided by the square root of 137, and this gives us about 0.8 feet per second squared in the direction of the normal component. And then, of course, when you add the two together, you would get back the acceleration vector. That was a pretty long one, so let's go ahead and take a look at example 3. Example 3 again gives us the path followed by an object moving in three-dimensional space with the vector valued function r of t, where the lowercase t, the parameters, time measured in seconds. And I guess we can assume in feet, it doesn't actually say. R of t is given by 1/2 t squared plus 1 in the I hat direction, t squared plus t minus 2 in the j hat direction, and t cubed minus t plus 3 in the k hat direction. Again, what we want to do is we want to split the acceleration vector into two pieces, one along the unit tangent vector and one along the unit normal vector, and then we want to evaluate at a particular point in time. Go ahead and pause the video to work these out, then turn the video back on and we'll compare our results. Hey, let's compare how you did. I'm not going to go into quite as much detail on this one, but I do want to point out a better way of doing multiplication of binomials when you have multiple terms you're having to multiply out. So I computed r prime of t, and I computed r double prime of t. To find the magnitude of r prime of t, the speed, what I did was I multiplied out the binomials, but I lined up like terms under like terms. Now I ended up with a 9t to the fourth, which I didn't leave enough space at the front, so I tucked it at the back. But when I rewrote it, I moved it to the front. And then I applied the formula that you see here, that the tangential component of acceleration is the dot product of the velocity vector with the acceleration vector divided by speed. And when I multiplied the dot product out, I came up with an expression of 18t cubed minus t plus 2 divided by the speed, which is the square root of 9t to the fourth minus t squared plus 4t plus 2. Not as nice a tangential component as we got in the previous problem, but again, it's not as difficult as the normal component, which is more difficult. Not easy, but not as difficult as the normal. To compute the normal, since I had the tangential vector, I chose to use that one. You may have chosen to use the fraction form instead, and that's perfectly fine. You should come up with the same solution. I have actually worked it both ways. It does work. In this case, I needed to find the square of the magnitude of acceleration. So I worked that out and came up with 36t squared plus 5. And then I needed to square the tangential component, which in the denominator simply took off the square root, but in the numerator gave me a trinomial squared. And again, I used this combination of rows and columns to line up like terms under each other. And I came up with this result here, 324 multiplied by t to the sixth power minus 36 multiplied by t to the fourth power plus 72 multiplied by t to the third power plus t squared minus 4t plus 4. When I put this into the formula, note that I'm going to be subtracting the square of the tangential component, which will basically change all the signs in the numerator. And then I can add them together. I have to get a common denominator, which is kind of a nasty process, if you can tell right there. And so I again employed this combination of rows and columns to line up my like terms. My final result was the square root of 45 multiplied by t to the fourth power plus 72 multiplied by t to the third power plus 66 multiplied by t squared plus 24 multiplied by t plus 6, all divided by the square root of the 9t to the fourth power minus t squared plus 4t plus 2. Again, that being the velocity, speed, magnitude of velocity. All right. So hopefully this has made sense to you. It's certainly not an easy process. It's rather complicated, very long, very easy to make mistakes. So take your time, use lots of space on the page. We want to turn our attention, now that we've split it into components, into an application problem, and this is projectile motion. So a projectile could be a bullet fired from a gun, it could be an arrow shot from a bow, it could be a baseball that you're throwing through the air, it could be a stomp rocket, right? Those fun little toys where you stomp on well, what do they call those? Oh gosh, it's escaping me at the moment. Anyway, it looks like an accordion. You stomp on it, it pushes the air and launches the rocket out. So it can be anything that you're projecting, throwing, shooting, whatever. All right, so we want to look at projectile motion as it travels through the air. We're going to neglect air resistance at this point in time. In physics, you will not be able to neglect it all the time. You will have to look at it. We will have to choose a frame of reference, and we're going to do what we've been doing in the three-dimensional space, which is we're going to choose our frame of reference to be at the point at which the projectile is launched. So in our case, we're going to be looking at an arrow shot from a bow. So we're going to set our frame of reference at the point where the arrow is released. So that becomes our origin, if you will. It's totally arbitrary. The formulas just have to change a little bit depending on where you set the origin. So it could be that you set it at the ground at the feet of the archer, or you could set it where I'm setting it, which is at the point of projection. All right. So again, we're going to allow the positive y-axis to be up, the negative y-axis to be down, the positive x-axis to be forward, that is away from the archer. And note that while the object exists in three-dimensional space, like the motion of the planets around the sun, the actual motion is in 2 dimensions. So it's traveling along a plane like this. It's not going back and forth like this, all right? So it's traveling in a plane. In essence, we can think of it as traveling in the XY plane with no component in the Z direction. The force of gravity is pulling the object down to Earth. So we can think of the force of gravity using Newton's law, F equals ma. So if we have F equals ma, then we have the mass of the object, which is m, multiplied by the acceleration. In this case, we're going to separate the negative from the gravity. It doesn't have to be, it could be included, whichever way you want to do it. I let gravity be 9.8 meters per second squared in the metric system. And I wrote it as negative mg in the j hat direction, because again, the arrow is being shot this way. It has horizontal motion and vertical motion, and gravity is pulling it straight down to the ground. So the motion is in the negative j hat direction, down. So what we want to do to find the different acceleration of this is we're going to take and we're going to integrate acceleration to get velocity. So we have acceleration as negative g in the j hat direction, all right, where g is a positive 9.8 meters per second. If we integrate the acceleration, we should get the velocity vector up to a constant vector. So what we do is we simply integrate negative g j hat, which does not have the parameter t in it at all, since negative g is a constant, negative 9.8. And this gives us negative gt in the j hat direction plus some constant vector. The constant vector is going to be pinned down by the initial value, the initial velocity, or the velocity at time 0. And that will give us the value of c. So if we call that v naught, and again, we say naught like NOT or KNOT, but it's actually naught, N-A-U-G-H-T. It stands for 0. So naught something is 0. All right, so this gives us an equation for the velocity of negative gt in the j hat direction plus the initial value of the velocity, that vector. Assuming the object is launched, thrown, shot, projected, whatever, upward at an angle to the horizontal. So we're going to assume it's shot upward and at some angle of theta. So in our mind, what we're actually envisioning, and I'm a terrible drawer, so don't, right? So the person is here and they have their bow and the arrow is shot straight. Well, okay, I've got my arrow going the wrong way. The arrow is being shot out this direction. All right. So we're setting the origin right here at the point of release. So the arrow is shot at an upward projectile, not straight out, because then it would just veer towards the ground. So you shoot up at an angle to theta from the horizontal. So notice the ground is actually down below our horizontal axis. The ground is actually down here. This is the ground right here. So you could have a bush right there. All right. So our horizontal is above that. And in this way, by setting the origin here, we can say that the initial height, of course, is 0, but it does have an initial velocity, and the velocity is applied at an angle. And you can see that here in this sort of I don't even know what you call that color, peach, I guess. You can see the velocity vector here as the diagonal of the parallelogram. And so we can break the velocity vector into two components, into a horizontal component, v naught x, and a vertical component, v naught y. So v naught x is the initial velocity in the straight horizontal direction, and v naught y is the initial velocity in the straight vertical direction. And then at any point along the arrow's path, you can see that the arrow goes up, reaches a magnitude where it hangs for a moment, where it's not actually moving at that one instant in time, and then begins to fall back to the ground. It's actually following a parabolic path. And at any point along the trajectory of the arrow, we can split the velocity vector into a horizontal component and a vertical component. Now notice that here at the apex, and apex of course just means, well, at the vertex of the parabola, at the highest point in the trajectory of the arrow, that at that one instant in time, it stops moving up but hasn't yet begun to fall. Because it's not moving up but hasn't begun to fall, the velocity in the y direction at that one instant in time is 0. But at every point, neglecting air resistance again, we can assume that the velocity in the horizontal direction is always that initial velocity in the x direction, v naught x. But the velocity in the y direction is changing. We have an initial velocity in the y direction, v naught y, here at our origin. But as it travels, gravity is pulling it down. So Vy, the velocity in the y direction, is actually decreasing or changing as we follow this path. Notice over here that when it reaches the plane of the horizontal, in other words, even with the height at which it was shot, which is not the ground, right? The ground is further over. So this is where it hits the ground here. But this point right here, which I put an asterisk, that point is when it reaches back to its initial position vertically. All right, at that point, we can say that the velocity in the y direction has to be exactly opposite to what it was in the initial moment of time. So it has to be negative v naught of y. It has to fall at the same rate at which it was fired from the bow, right? Which is a reason why we don't shoot bullets in the air. What goes up must come down, and it comes down, neglecting air resistance at exactly the same speed at which it went up. This is a really bad idea. Every time I see this in movies, I just think, so who gets killed? All right, and that does happen. I actually lived in a city where someone shot off a gun on the 4th of July and killed a 3-year-old child 1 mile away. And they were able to find the location where the gun was fired based on the trajectory of the bullet through the body of the child. They were able to tell that it was a mile away, and they knew where it was fired from, but they never did catch the person, who probably wasn't even aware that the bullet they fired in the air killed a child. All right, so we're breaking our initial velocity into two components, v naught cosine theta in the I hat direction, v naught sine theta in the j hat direction. That's because our arrow is shot at an initial angle of theta, and we know that this forms a right triangle with a right angle right here. Let me put my right angle in right there. And we know that v naught is the hypotenuse, and so the sine of the angle is opposite over hypotenuse. So the opposite is going to be the hypotenuse times the sine of the angle, right? Which is basically what we have here, v naught sine theta. So we've split our velocity vector into two components, one parallel to I hat and one parallel to j hat. If we integrate velocity, that should give us position. And then to find the constant vector that you get as a result of integration of a vector valued function, you want to let t be 0 and find out something about the initial position. So in this case, our new velocity vector is given by negative gt in the j hat direction plus v naught. And when we integrate that, we get negative 1/2 gt squared in the j hat direction plus v naught t plus a constant vector. If you've taken physics, you're like, oh my gosh, it's the formula. I use this all the time. Yes, this is the formula and where it comes from. Then we can let S naught represent the initial position of the arrow, which if I put the origin at the moment where it's shot, the initial position is 0, all right? The ground would be a negative position, but the initial position would be 0. And this gives me the formula for position, negative 1/2 g times t squared in the j hat direction plus v naught t plus s naught. Let's now take a look at the position vector by splitting v naught into its two components, one parallel to the x-axis, one parallel to the y-axis, I hat and j hat respectively. So this actually gives us two components in the j hat direction, v naught t sine theta minus 1/2 gt squared, and one component in the I hat direction, v naught t times the cosine of theta. So this gives us the position vector, which will tell us where the arrow is at any particular point in time. Now, what is the range of motion and how does that compare with the altitude? So when we're thinking about range of motion and altitude, range is the maximum horizontal component of the projectile, how far it travels from the point at which it was shot until it again breaks that line of where it was shot. So it's not necessarily when it hits the ground. Instead, the range is measured out. Let's see if I have a picture for the range. I can draw it on our picture up here. The range is actually measured here. Right? This is the range, right? So it's measured from the horizontal axis back to when it again hits that horizontal axis. So the range is the maximum horizontal distance it travels from when it is initially shot until it comes back to the same height at which it was shot. Now, to hit the ground is going to be a further distance. It'll be the range plus this little bit of distance that you see here on the ground. So that's slightly different, and we are going to need that. Now, altitude is the distance of the projectile from the plane at which it was shot. So again, from the horizontal. So the altitude is measured here. So let me put altitude onto our picture in a different color so that you can see it. This is the altitude, which again is not the distance in this case of the arrow from the ground. So it depends on how you define things, and you have to be careful to give the correct response based on the question. All right, let's take a look at example 4, our last example in this section. So we have an archer who fires an arrow at an angle of 40 degrees above the horizontal with an initial speed of 98 meters per second. Yes, I chose numbers to make it slightly easier. It's still not easy. The height of the archer is 171.5 centimeters, which you should recognize right away that if this is in meters, this needs to be written in meters as well. So we're going to have to write that as 1.715 meters. We want to find the maximum height of the arrow from the ground, which is not going to be the altitude. It'll be the altitude plus the height at which the archer shot the arrow. And then we want to find the horizontal distance the arrow travels before it hits the ground. Again, if I place my origin where it is projected, then the range only goes back to the same height from which it was shot. To hit the ground, it travels a little bit further. So you can choose to put the origin either at the feet of the archer right here, or where I'm going to place it, which is up here. Regardless of which way you do it, the trajectory of the arrow is the same. It simply changes the values of S naught. All right, so if you set the origin on the ground, then S naught would be 1.715 meters, all right, in the J hat. And this would need to be included in the formula that we did up above. So first we want to find the maximum height that it reaches above the ground. And that maximum height would be given by this point right here. So it would be the height of the arrow at the apex of its trajectory down to the horizontal, plus the height at which he shot it. So we actually have two little segments. We have this segment here, and then we have this segment here. So let me do this in a different color, down to the ground. So the maximum height of the arrow is composed of those two different segments that we'll add together. Now, this pink segment is the 1.715 meters, the height of the archer as he shoots it, roughly, more or less, is probably, what, 6 centimeters less because he didn't fire it at the top of his head, but pretty close, all right? So when we're looking at this, we need to find the altitude, which is the measure of the blue mark right up there. The horizontal component of velocity is not 0, or it wouldn't keep traveling away from the archer. So it has both a vertical velocity, which is causing it to travel up before gravity causes it to fall down, and it has a horizontal component, which is pushing it away from the archer. Right? So we want to find the altitude when the arrow reaches that apex. And we know when it reaches the apex that at that one instant in time, it's not moving, which means that the y component of the velocity at that one instant must be 0. And that's what's going to let us find it. So we start with our formula of what we were given. This is our formula for S of t. And in this case, we have V naught T cosine theta I hat plus the quantity V naught T sine theta minus 1/2 GT squared in the J hat direction. And again, our angle theta is 40 degrees. Our initial velocity is 98 meters per second at that angle of 40 degrees. And gravity is 9.8 meters per second squared. If we substitute these values into the formula for our position vector valued function, we come up with the equation that you see here. And then we take the derivative to get the velocity vector. Remember, at the apex of the trajectory, the velocity in the y direction is 0, not in the x direction, or it would just fall, right? It still was traveling forward away from the archer, even at that point in time. So the velocity is not 0 there at the apex. The y component of the velocity is 0. So when we take the derivative and we plug all of this in, we can take the vertical component of the velocity, which is the part in the j hat direction, and we can set it equal to 0, right? It's neither moving up nor moving down. And this gives us basically, when we solve for time, that it's at 10 times the sine of 40 degrees seconds. That's when it reaches that maximum height, all right? So at that time, we want to know the position. The position will tell us the altitude, again, measured from the horizontal from where it was shot, because that's where I put the origin. So when we plug 10 sine of 40 degrees into the position velocity vector, or position vector valued function in place of time, we come up with 482.56 meters plus 202.46 meters, all right? This is the position from the horizontal to the apex, the small little blue mark I made earlier. But this is not the measure from the ground, all right? Remember the way that I set mine up here in our picture, scrolling right here. What I've found is the altitude here measured from the horizontal where I place the origin. The ground is 1.715 meters below that. So the height above the ground will be that altitude that I just found plus 1.715 meters. Right, so let me go ahead and get down to that part of it. That gives me a total of 204.18 meters in the j hat direction. Yes, I've also got a component in the I hat, but I'm interested in height above the ground, which is just the j hat component. All right, so just the y direction. So I took the value that I got for the altitude, how far above the horizontal it got shot, plus the distance of the original horizontal from the ground, and that gives me roughly 204 meters above the ground, which does not sound reasonable to me at all. I don't think an arrow is going to go that high, but at any rate, that's what we got. Now we want to find the total distance traveled horizontally. Now the range, again, is measured from the place where it is shot back until it reaches that horizontal line again. But we want the distance for it to hit the ground, so it's going to continue traveling until it hits the ground, when the position is a negative 1.715 meters, right? So that will give us the position in the y direction. Right? And we want to find the x component at that point. So that's one of the keys to recognize in order to solve this one, is to recognize that at the instant the arrow hits the ground, since this right here is where our axis is, this distance right here is a negative 1.715 meters. All right. So the position in the y direction at the instant it hits the ground is that negative 1.715, all right? Okay, so this is not the range, all right, but rather the range plus a little bit more, right? So we start again with the position vector equation. We know the arrow will hit the ground when the height of the arrow in the y direction is negative 1.715, right? So below our position of having fired it. So we take the y component again, which is this expression here, and we set it equal to negative 1.715, which unfortunately for us gives us a quadratic equation in t with very nasty components. And yes, I'm sorry, but you do have to do the quadratic formula. So your A is 4.9 meters per second squared, B is negative 98 meters per second times sine of 40 degrees, and C is negative 1.715 meters. Again, that's the distance between what we used as the horizontal plane down to the ground. And notice that I did move a couple of the terms to the right side of the equation so that my A had a positive coefficient, which is why it stayed negative 1.715 meters. Now, it's a pretty nasty quadratic formula. I will not lie to you, it's pretty nasty. But when you work it out, you're going to get two possible t values, one with the plus, one with the minus. The one with the subtraction sign is going to end up being completely negative. And when you do that, that doesn't make sense in this application problem since t represents time. So we can ignore the negative root and take only the positive root. So if we move on in the lecture notes to the last page, you'll see that the positive root leads to about 12.88 seconds or about 12.9 seconds. Then you rewrite, of course, the position vector equation, vector valued function, and you substitute in this approximate time of about 12.88 seconds. And when you're done, you end up with the horizontal component of the movement being about 967.15 meters. All right. So this would be the end of this particular problem. And this says v sub x, which it should be s sub x. So let's go ahead and make that change right here so that we make sure that we know it. This should be s sub x. That would be the horizontal component of the position vector. And this is the distance it travels from the location of where the archer fired the arrow until it hits the ground, which I think is completely unrealistic, but I don't know much about archery, so maybe it is realistic with a compound bow. So this is the end of the section on projectile motion, and we'll be ready to start chapter 4. Chapter 4, we veer away from vectors a bit, and we start looking at real valued functions of more than one independent variable. And to start off, of course, we'll talk about quadratic surfaces again, which are examples of functions of multiple variables. In other words, the function is a function of x and y and gives us the value of z. But they're not vector valued functions, they're just scalar valued functions. So I hope you'll join me for chapter 4 coming up next.